All right, so hello. So we're gonna build off what we did yesterday, which was making Lewis dot symbols, and now we're gonna look at what we call Lewis dot structures. Okay, so if you remember, our symbols were only for a single atom. Okay, when we get to something called a structure, so a Lewis dot structure, this is where we're gonna have multiple atoms. So what's known as a molecule or a compound. So something with multiple atoms in it. Okay. But again, what it is a diagram that uses the dots to show the valence electrons. So nothing's really changed in how we draw them, okay? The only thing that's changed is now instead of having one atom, we have multiple, okay? And why I want to do this is because this helps us visualize how our valence electrons are being shared when we form these covalent bonds, okay? So remember in covalent bonds, we're sharing electrons. And so these Lewis dot structures help us look and say, okay, what is sharing with what, all right? And so our rule that's going to govern all this is something that's known as the octet rule, okay? And so our octet rule is that our non-metal atoms, or things that make up covalent compounds, are going to combine so that each atom has a total of 8 valence electrons, okay? And so they're going to get to this number 8 by sharing electrons. So remember that our ionic compounds also wanted 8 valence electrons, but they got to there a different way. Okay, so they either stole someone's electrons or they gave up their own. Okay, our non-metal atoms are going to share them instead, but the goal is still 8 valence electrons. All right. And so where this name comes from is an octet means 8. Okay, so each atom in the molecule or compound has to have an octet of valence electrons. Our one exception is hydrogen. Okay, so hydrogen atoms do not like to follow the rules. They do not follow this octet rule. So they only want a total of 2 valence electrons. All right. So when we are drawing these, we want to make sure that everybody has 8 except for hydrogen. It's always going to have 2. Okay. And so if we look here, we're going to look at a lot more of these. Okay, but this is just an example of, okay, what's going on. And so here are some different compounds, some different molecules where they're bonding to different things and they're sharing electrons. Okay? And so what you can see, if you look at each of these, if you go into each circle, okay, so like each circle is showing our individual atom. All right, so like in this one, there's 3 chlorines and 1 phosphorus. If you look at each circle contains 8 valence electrons, which is our goal, right? But what these overlapping circles again mean is that those electrons there are being shared. Okay? It's not like this chlorine is stealing from the phosphorus. These atoms, this chlorine, this phosphorus, are sharing those electrons equally. All right. And so just like I did for these symbols, I'm going to give you a little path to follow. Okay. And so the first thing you want to do is make sure you draw the symbols for each atom you are given. Okay. And so why I was so strict and why I mentioned it so many times that you didn't want single electrons is because our goal when we bond these, okay, is not to have any single electrons anywhere. And so a covalent bond requires 2 electrons. And so you want to look, once you've drawn all the symbols, to think, okay, how can we fit these together to get this goal of not having single electrons? All right. And so the analogy I like to use is like a puzzle piece. Okay, so that will make sense when we start to do these, but you want to look and say, okay, how can I get rid of my single electrons? Some other just rules to be aware of: the center atom. So we have multiple atoms now, so we need to position them correctly. The center atom is always going to be carbon, okay? But if we don't have carbon, all right, it's going to be the element we only have a single one of, all right? Again, that'll make more sense when we start doing these. Another thing is that our hydrogen atoms are always going to be on the outside. So our carbon will always be in the middle, our hydrogen will always be on the outside. And then once you think that you piece these all together correctly, you want to just check. Okay, remember that we want these to fit the octet rule. So we want to make sure that after we draw them, that they each have 8 valence electrons. All right. So just like last time, we're going to go through and we're going to do some examples. Okay. And so the first one is CH4. So our first one is CH4. So if you remember, the first thing we want to do is we want to write each of the individual electron dot symbols, okay, or Lewis dot symbols. So this is just what I did yesterday. Okay, remember I just find the number of valence electrons and I draw them as dots. So remember, like in this one, that I want to make it so that I only have single electrons to begin with and then only pair them if I get to 5 or more. All right. And so now what you want to do is you want to look here and be like, okay, we don't want single electrons. All right. So after we've drawn all the symbols, we want to get rid of our single electrons somehow. And so you want to look and be like, okay, how could we, using the pieces that were given here, get rid of our single electrons and get 2 electrons in each of these 4 locations? Well, if you look, there's 1 electron in each location here, okay, for the carbon, and then each of these hydrogens only have 1 electron. So if we just move this hydrogen over here, now we have 2 electrons in that location. All right. So what I'm going to do is I'm going to draw it with how it's going to bond. And so I'm using the different colors here because I'm trying to show you that the different colored dots are the electrons that are coming from that colored atom. So example, this blue one, this blue electron is coming from that hydrogen. But what we see here, okay, is that we're sharing electrons, right? So in this location, there's a black electron and there is a blue electron, all right? So one is from the hydrogen, one's from the carbon, but both the carbon and the hydrogen are now sharing those 2 electrons, all right? And so now we're like, all right, we don't have single dots anywhere, single electrons, so we're happy, okay? And we also want to look and be like, is everybody happy in terms of having an octet? So we look, we're like, okay, the carbon has 2, 4, 6, 8 electrons, so it's happy, all right? So carbon is good. And then remember that our hydrogen atoms only like to have 2 electrons. And so since each one has 1 black electron and 1 blue electron, now they each have 2, all right? So this one we're happy with, all right? So let's do our next example. So our next example is F2. All right. So in this case, again, we want to look and be like, okay, well, let's draw out our individual symbols for each of these. And so I know it might be repetitive. You're like, okay, well, fluorine's the same. Why can't we just draw one of them? Because you want to draw everything because you want to see how it can easily fit together, how you can easily visualize it. And so if you look on the periodic table, fluorine is in group 7, so it's going to have 7 valence electrons. Okay, so I'm going to draw 7 dots around it. Again, notice that I'm only starting with single electrons in each location and then drawing 2 of them, okay, pairing them when I have to, all right? So if we look now, there's 1 location on each of these, okay, that has a single electron. So right here and right here. And so now what we want to do is think about, okay, well, how can we combine these to get rid of that single electron? Well, if we take this fluorine atom and move it over here, all right, now if we share those 2 single electrons, we could have something like this. And so I'll draw the other fluorine in a different color just to show you, okay, so I'm drawing this fluorine right now to show you that its electrons, or which ones are its electrons and which one came from the black fluorine. Okay, if we look here, we see that, all right, now we're sharing these 2 electrons, okay, and there's no single electrons anywhere, all right? In each of our 4 locations, there's at least 2 electrons. And then you want to look and be like, okay, well, is each fluorine happy? Does it have 8 valence electrons? Well, there's 2 here, 4, 6, and then it shares these two, so 8. All right, and so that's the same for this fluorine, and so we're like, all right, cool. All right, so we have a full valence shell for each of these. All right. And so our next example is NH3. So NH3. And so if we look at the periodic table, we'll see that N is in the 5th column. Okay, so it's going to have 5 valence electrons. And then we have 3 hydrogens. Okay. So our hydrogens just have a single electron. So then we can look here and be like, okay, well, where do we have single electrons? Well, each of the hydrogens has a single electron, right? And then there's 3 locations on the nitrogen where there is a single electron. Right, so remember, we don't like those single electrons. We want to pair them up. We want to get rid of them somehow. So if we put a hydrogen at each location, we get rid of those single electrons. So again, we have our nitrogen. And I'll draw the hydrogens in a different color. So you can see that, okay, now this nitrogen and the hydrogen are sharing these electrons, this hydrogen and the nitrogen are sharing these, and this hydrogen and the nitrogen are sharing these. Okay. So then you want to look and be like, okay, is each hydrogen happy? Yes, because they each have 2 electrons. And our nitrogen is happy because it's sharing these 6 electrons, and it also has these 2 right here that aren't being shared. Okay, and so things that are not, or a pair of electrons that is not shared is known as a lone pair. So that is what these are called. So this pair of electrons that is not bonded to anything else is what's known as a lone pair. All right. So our last one is water, so H2O. So we have oxygen, okay, which if we look on the periodic table has 6 valence electrons, okay. So we'll draw it with 6, and then each of our hydrogens has 1 again. All right, and so just like last time, we're going to look and be like, okay, how do we get rid of these single electrons? Well, there's a location with a single electron there, there's a location with a single electron there, and then we have a single one on each of these hydrogens. All right, and so to get rid of them, just like putting together a puzzle, we're going to snap one on here and snap one on here. Because then if we look, draw our oxygen again, and then we can add in our hydrogens. Okay. So then we can look and be like, all right, is everybody happy? Well, these hydrogens have 2 electrons, okay, so they're happy. Our oxygen is sharing 2 electrons with each of the hydrogen, so 4 total, okay? And then it has 4 up here, okay? And remember that these are known as lone pairs, okay? So again, the oxygen is happy. It satisfies the octet rule because it has 2 lone pairs, so 4 electrons there, and then it's also sharing 4 electrons, so 8 total. Okay, and so again, just to reiterate, things that are not shared, the electrons that are not shared are called lone pairs. So here is another example of a molecule. So this is hydrogen chloride. And so here, the chlorine is bonded to a hydrogen atom, okay? But it still has 6 electrons that are not bonded to anything else, okay? And so the things that are, the electrons that are not bonded are known as lone pairs, all right? So just like last time, you have a worksheet that asks you to draw on a separate sheet of paper 5 different compounds or molecules, all right? So again, you want to make sure, are you fulfilling the octet rule? And are you getting rid of your single electrons? All right, so that will be your homework.